As usual, hindi naman natin sasagad hanggang 9. And to start with our lesson for today, we will first have a recap of what we discussed last week. Magkahawak.
General math daw, in the modern world daw. I-deliver parcel derivatives. Yung mga big ng science.
Okay, so we started our first meeting last week by the introduction of the MEPAR 1 2 course, the discussion of the course information syllabus, and I started with the lecture on the introduction of machine elements, and also we discussed how to compute for mobility using the Grabler's equation. I talked about what is a kinematic design, how it is done. For example, using a complex machine or a complex mechanism, we can represent its kinematic design using a kinematic diagram. The kinematic diagram is as simple, for a simple description, it is the stick figure of a mechanism. So we can better visualize or understand how it moves. Sample of the mechanism parts that we will discuss in this course is cams. So with cams, we will discuss the design of cams and follower on the second half of the course, so after midterm. This is a sample of how a cam moves with its follower. And I also introduced to you gears. So on the later half, on the second half also of this course, we will design gear tooth profiles. Then gear trains. Gear trains is simple as the pairing of gears in the transmission of rotation motion. I also discussed to you the difference between a mechanism and a machine, and the four major types of motion. We have plane motion, we have helical motion, and spherical motion, and spatial motion. And under the plane motion, we have rotation, we have translation. I also discussed to you the difference between reciprocating and oscillating. For the motion of a mechanism, since a mechanism's movement is repetitive, when we complete one motion of the mechanism, the complete motion of a mechanism, we will call it a cycle. The time it will take to complete the cycle is the period, and the part by part movement to achieve the cycle is what we call the phase. I discussed to you the different types of links, the mating links or the pair links. We have the lower pair, the higher pair, and also I described to you what is a link. It is a rigid body having two or more pairing elements. So at both ends, they have a partner. I discussed to you the mobility. So the mobility is the capability of a mechanism on how to move. It moves on the x-axis, the y-axis, and the rotation movement. And I taught you how to compute for the mobility using Grabler's equation. Again, Grabler's equation is used to determine if a design or a mechanism has the capability to move. Because in the past, designing is only performed by hand or by simple CAD, and there were no simulations on the CAD applications. Meaning, they will have to make prototypes of the mechanism to determine if it has a capability to move. So instead of making a prototype already, they came up with the Grabler's equation in the past to compute if the mechanism has the capability to move. So the Grabler's equation is represented in m is equal to 3 times the quantity n minus 1 minus 2f1 minus f2, where m is the mobility and its unit is degrees of freedom. N is the number of links of the mechanism. F1 is the number of 1 degree freedom joints, and F2 is the 2 degree freedom joints. For the difference between 1 degree of freedom and 2 degree of freedom, we have this table. So this table, we have 1 degree freedom, are classified as revolute, prismatic, or rolling contact joints. For the 2 degree freedom, we only have cam or gears, rolling and sliding. So when we compute for the mobility using the Grabler's equation, if we get an answer which is greater than or equal to 1, the device or mechanism can move because it has m number degrees of freedom. If it is 0, the device is statically determinate structure. For example, this example, the mobility is computed as 0 for this figure 1.16. But it does not mean that it cannot move. By looking at it practically, we can imagine that this mechanism can move. Then, if we get an answer which is less than or equal to -1, it is surely that the mechanism has no capability to move. We have the sample computations here. So for this first 4-bar linkage on the figure 1.18, we computed the mobility and we gained the answer as 1, which means this mechanism has 1 degree of freedom. But on the second example, which is figure 1.19, we have computed the mobility and we got the answer of -1, meaning it has no capability to move. And to give an example on how to identify a joint with 2 degrees of freedom, we had figure 1.20, whereas we have two cams or a cam and a follower, which is paired at this common tangent. They are in contact, they are rolling and sliding to each other. So the contact of link 2 and link 3 is counted as an F2. Then for further discussion of the computation of mobility, I gave practical exercises or recitation, which Miguel, Russell, Lucelle, Alvin, and Seren Adham had helped us in computing. So that's what we did last week. So before we proceed to the next topic, does anyone have any clarification? Siyempre wala, sir, naiya kami magtanong. Pwede man kayong magtanong, man. Mukha ng mga approachable si sir. Ba't may mukha? Hearing none, no more further questions with regard to our topic, I'll proceed with the discussion of our new topic, which is the 4-bar linkage motion and Grashoff's law. So what is this? 4-bar linkage motion and Grashoff's law. One of the most basic types of mechanism is what we call the 4-bar linkage. By the name itself, it's a mechanism with 4 links. We just call it 4-bar, meaning the link should be bars. So one link cannot be a gear, one link cannot be a slider or a cam. So every link must be a bar. So for our 4-bar linkage, to design a 4-bar linkage, we must follow what we call Grashoff's law. So Grashoff's law, it determines if the mechanism can move as intended. So the Grashoff law states the limitations of the 4-bar linkage on what should be the correct lengths, because there's a guide on what are the correct lengths to be used in making the 4-bar linkage. These are samples of 4-bar linkage. The circle here is not actually a link that is a circle. The circle here indicates the motion of the link. Meaning, if we have a link 2, and at the end of link 2 is point A, and point A travels on a circular motion, it will create this circular path. So again, this is not a circle link. This is not a circular link. This circle represents the travel of the point A while link 2 is rotating. Here we have link 4, where at its end we have point B, and its travel is only this arc. So it's not a complete rotation, just like here in link 2. And this arc represents the travel of point B. Same as this one, for 4-bar linkage, this circle represents only the travel of point A and point B. And let's go further into that. For example, we have a 4-bar linkage here. Imagine only these parts. So this one is link 2. This one is link 3. This is a connecting link or a connecting rod. And this one is link 4. When you imagine this kind of setup, it's called 4-bar linkage because all the links are bars. But the fourth link is always the ground. So, even though number 1 is technically a bar or a link, since we always count the ground as 1, so the other links must be bars. So that's why it's called 4-bar linkage. But technically, there's only 3 bars. Then for another example, for this example, these are unequal lengths of the bars. Then for this example, these are equal lengths of 2 bars of opposite. So here we have link 4 and link 2 opposite each other, having equal lengths. Then for link 3, parallel to the ground, it also has an equal length. So we can have a 4-bar linkage of this setup. We can also have a setup of 4-bar linkage where there are unequal lengths again, but the center distance but where the distance of the ground is close to each other. So what's different here from the earlier example is link 4 can also make a full rotation. Meaning, if we close the gap of the ground links, we can have the other link have also a full rotation. In comparison with the earlier, if the link to the ground is too far apart, link 4 can only make an oscillating motion. It cannot make a full circle. But on a 4-bar linkage where the connection to the ground is close. Wait. Why is it stuttering? Uh, when the link to the ground is close to each other, the link 4 can make a full rotation. So how close are we talking about? What are the guidelines to make sure to follow that these links will make full rotation by having the link to the ground close? We have to follow these three rules. So O2 and A and O4B must be greater than O2, O4. So what does it mean? O2A is this O2 and this A. So meaning O2A is linked to. Then O4B is this one, O4 and B, meaning O4B is linked 4. Meaning their length must be greater than O2, O4. Whereas O2 and O4 are the distance between these two joints. Again, O2A describes this link 2. O4B describes link 4, meaning O2, O4 describes the distance between these two joints, O2 and O4. Then they must also follow this rule, O2A minus O2O4 plus AB must be greater than O4B. So again, just clearing this out. O2A is linked to, O2O4 is the distance between the two joints, O2 and O4. Then their difference added to AB. AB is the third link or link 3. Must be greater than O4B, which is link 4. Again, what I'm talking about as these formulas or guidelines, these computations must be followed if we want to have a 4-bar linkage, whereas link 2 and link 4 can make a full rotation. And another guideline to follow is O4B. The difference of O4B and O2O4 when added to O2A must be greater than AB. Meaning, O4B, which is link 4, wait, I'm just gonna clear. O4B, which is link 4, O2O4, which is the distance between the two joints, O2 and O4, and when added to O2A, which is link 2, must be longer or must be greater than the link AB. AB is link 3. Okay? Again, I will repeat. This is a 4-bar linkage, whereas link 2 and link 4 can make a full rotation. And to design this mechanism, we should follow these relationships where O2 and A and O4B must be greater than O2, O4. So this is not addition. It means O2A must be greater than O2, O4 and O4B must be greater than O2, O4. Then also, another guideline is O2A and O2O4. The difference of this when added to AB must be greater than O4B. Then O4B minus O2O4 plus O2A. The difference of O4B and O2O4 when added to O2A is greater than AB. You can use these guidelines when designing 4-bar linkages with this requirement. When you encounter a design of a mechanism and that would require the rotation of both links, but they do not have the same length, you will have to follow this. Because if it has the same length, we can just go with this one. They can also make 2 full rotations. So that's
I'm not
the
really
four-bar
interested
linkage.
when it comes sa mga
So we have what
stickers
we call the
versus
characteristics of the four-bar
pero
linkage.
expect ninyo na you will be answering
We have what we call,
plenty of
again, the characteristics or
doon
characterized.
kayo mapapractice.
The motion is
And
characterized into what we call the
once na
crank
magaling kayo
rocker,
solve yung problem set, you
double
will
crank,
eventually
or
get the good grades
double
in
rocker.
studies.
So what are these? Crank
So
rocker
this will be a
is the motion of one rotation and one oscillation. And figure A, link 2 rotates while link 4 oscillates. So it's just rocking back and forth on a certain arc. So link 4 is rocking at this arc path
for the online class,
while link 2 is rotating on this circular path.
You would take
So we will call it
a little
crank
bit,
rocker. In this motion, it is usually linked to, which gives off the motion. It has a rotation motion that it influences link B.
First is we need to illustrate
So that's an example. Then, in some cases, the rocker or this link 4 gives a rocking motion and it rotates link 2. But it is rare.
This INO will be measured.
Crank is always defined as the one giving the motion. So that's why when we have crank rocker, it is crank. This rotating link is the one that gives the motion to the whole mechanism. So it is the source of the motion.
This will be computation test.
For double crank, we have
There were nilalabas sa exam na objective.
links that can make two full rotations. So this one, link 2 can make a full rotation. Link 4 can make a full rotation. So another, for this example, when we have unequal lengths, but the links can also make full rotations, we have to follow the guidelines. So for this example, we can call this double crank because they can rotate on a whole circle. Compared with the crank rocker, the rocker arm can only rock on a certain arc. So that's what the difference of crank rocker and double crank. And crank, sa keyword, since crank starts with the letter C, meaning its motion can make a full circle or a full rotation. So double, when we say crank rocker, we have a crank that can make a full circle. Then double crank, we have two links that can make two full circles. Then we have the double rocker. Whereas the four-bar linkage, the links, none of the links can make a full rotation.
Just be careful and
So si rocker, we have link 2 that oscillates on a certain arc, and link 4 oscillates on a certain arc also. So this is what happens when the joints O2, O4 are too far apart. The distance is too great, and it makes none of the links make a full rotation. So there are mechanisms in which require any of this, depending on what machine or what design you are doing. Right now, at least you know the terminologies. If you are to design a crank with a oscillating follower or as oscillating link, we will make a crank rocker. If we will have links with two full rotations on links, we have double crank.
So for the examination,
then if we have, if our mechanism requires rocking motion only, no rotation, we can have the double rocker.
Unless it is very
So this is the characteristics of four-bar linkages. So what is Grashof law?
There should be an
Grashof law
before you tell yourself
is
na,
this one. This is the guideline. So this is not
"Oh, hindi
actually
pwedeng
a
nagsabi ka
formula
lang sa
like
akin
Boyle's law or
na
gas
hindi
law.
ka exam."
So by Grashof law,
Hindi ka nakaregister.
it's a guideline
Kailangan ko siyang i-apply.
on
You can do that.
what to follow in designing a four-bar
I
linkage.
prefer email.
So
I-attach niyo
as a
yung-
means of determining whether a four-bar linkage will operate as a
Hindi
crank
naman
rocker,
i-stick doon,
a double
basta
rock, or the double rocker.
i-inform niyo ako kasi,
This is what we should follow.
doon ko rin para
If the sum of the lengths of the longest link and the shortest link is less than the sum of the lengths of the other two,
academic dishonesty
there will be formed. Okay, so this describes only the four-bar linkages.
I will let the proctors do their task para dito. Pag nahuli kayo ng
So that's
proctor,
four-bar linkages and Grashof's law. Just to summarize again, in
hindi ko na
design of mechanisms in
talaga siya.
machine design as
Ang
a
magiging
start,
punishment niya,
when designing a machine, we start with parts and parts only, up to going to the whole machines.
Pag nag-zero ka,
And in the design of mechanisms, where we have four-bar
pero
links,
kung
there's a characteristics. We have what we call the double rocker, the double crank, and
around,
the crank rocker.
talaga nahuli kayo, zero
To
talaga.
identify which one is the crank is the link that can perform the full rotation, while rocker only moves back and forth on a certain arc.
Kailangan yung inform.
And if we have to follow the design, our guideline is what we call the Grashof's law. So that's four-bar linkage and Grashof's law. Then we go to our next topic, which is what we call the vector operation.
And
So after this vector operation, we can end the class for today and we'll meet again tomorrow. For tomorrow,
makakatulong talaga.
it's an even week.
Talaga alam kung saan kayo pupunta.
So, we have class on boiler room. We are scheduled at boiler room. So it's the first time we will meet. So you will have to, guys, you will have to prepare a talent to showcase, to share to everyone. So you can like, hi, I'm Lucel, and this is my talent. I will sing Pantropico a cappella. So we can do like that tomorrow. Hi, I'm Adham. I am learning my Filipino languages and I will make a Filipino poem for you guys.
That will be from
So,
week one.
Adham, you should prepare also.
In case na, so this is a objective session. So, wala pa tayong computations dito. We will say some formulas, some theories. However, it is not something na...
Vector operation in analytical and graphical method. Again, after this topic, we can dismiss already. What is a vector and how does it relate to our topics?
On layman's term, when we say energy balance, what comes
Scalar
in
and
comes
vector.
out. Meaning kung ano yung pumasok, siya rin yung
I think you've already encountered this
whether it
vector
would be a
on other
energy,
science
it would be
subjects
energy
like
loss,
physics
it would be
or
heat loss,
on
steam
deformable
loss,
bodies. A vector is a
so those
representation
are the things. So,
of
this is
magnitude
just
and direction.
what
Because when we say scalar quantity, it is a magnitude only. We have
then
force, we
we
have weight, we have speed. So if we have scalar quantity, we can have as much as 1 foot or unit of length, 2 pounds or unit of mass or unit of force, and so on.
Then
But
after that,
if we have a scalar quantity with direction and sense,
so I think
how do we represent it?
on your physics
We can
class,
represent it
pag-aralan niyo
using an arrow.
pa, it's just a,
So if we have, for example, we will say we have 2 kilonewtons
may mga constant.
going down
Eventually naman,
or going south. We have a direction and we have the intensity or the scalar quantity of the parameter.
So this is not a final.
So vector, using vectors, vector is basically an arrow which represents force, velocity, and acceleration. Here in machine elements, we will use it as a representation of velocity and acceleration. Because in machine elements, we are not concerned anymore with the forces acting on mechanism.
Ideal gas process, isobaric, isometric.
How do we use vector in representing
And
velocity and acceleration?
this process do have certain formula.
We use a line
O, expect mo
with
na yung
an
mga
arrowhead.
formulas dito,
So this shows the direction sense. So what are the parts of the vector? We have the length of the line.
So yan yung
The length of the line is proportionate with the magnitude of the parameter. So if we have an representation of velocity using vectors, if we have vector here and vector another vector here, we can deduct that this has higher velocity than this one because it has a longer vector. So that's how we represent velocities in vectors. So the length of the line, this part, determine or shows the magnitude, meaning how fast, how quick the vector is. The next part, we have the direction in which the quantity acts, meaning
really appreciate those.
the arrowhead
There are jack of all trades.
points out the direction. So we have the arrowhead here.
Kasi kalimitan naman sa mga item nasa management.
Then the initial end of the line or the origin or the tail, this one,
Kung wala ka man ng background.
is the start of the motion. So this is the source of the motion. So if we have a vector that represents velocity and it is connected to a machine part or a mechanism, meaning we should place the vector on the machine part that is moving. So I will discuss it later on the next topic. But again, let's go to the parts of the vector. We have the length of the line, which shows the magnitude or the scalar quantity of the vector. We have the arrowhead
Do you have any questions?
to indicate the end and the direction.
Do you have any questions?
We also have the initial end or the tail or the origin, which indicates the source of the motion. So there's also one, the direction of the line is parallel to the direction in which the quantity acts. The direction,
For
it is mostly represented on the angle of deflection here. So what is the angle? And the arrowhead represents the continuous toward motion of the vector. So that's four parts. So again, the length of the line, the angle or the direction of the line, then the arrowhead, the sense of the quantity. So in which direction is it going to the right or going to the left, and the origin or the tail. So that's four parts of the vector.
Right, so pa-introduce naman yung mga sarili ninyo. So, base natin
Using
sa
vectors,
Chevy,
we can represent velocity and acceleration. So we will use it here in machine elements in the computation of velocities and acceleration. So the representation of this will mainly come from graphical approach. So you will have to have your own ruler, you will have to have your own protractor. So when drafting, especially in design plate and the midterm exam, you will have to draw the vectors on the points where it is identified to have one. Then, where do we place the vectors on mechanisms we can place the vectors and mechanisms at points on what we call a space diagram. So imagine figure 3-2. This is a link. This is an irregular shaped link. Imagine this is an irregular shaped link, and this one has
Start tayo kay Mr.
specific points where it is needed to identify the velocities. So at points A, B, C, we have to determine the velocity, we have to determine the acceleration. So the next one is to identify uh, how do we identify the velocity? How do we represent the velocity? So to represent the velocity, we will have to put vectors here. Also with points B and point C, so to represent the velocities acting on these points, what we can use is what we call the vector. And the space diagram is the body which we can represent the mechanism, or a machine part is a part of the machine or a part of the mechanism. We can use a space diagram to represent this. So this is how one example on how we can use a vector to represent the velocities acting on the points A, B, and C. So the velocities here must be coherent, meaning if they are, if the direction of the velocity is here, pointing here, going to the right, to the upper right, the velocity of is going here, the velocity is going here, meaning we can assume that this link has a joint at this point. And this link makes a rotating motion, whereas these vectors are acting on it. So that's what we call the position of vectors. When analyzing vectors, we can disregard the space diagram to determine a resultant. So vectors acting on a single link or a single part can be represented into a single vector. But before that, we can represent the vectors only on a vector in a diagram, whereas the vectors are only concerned. So we eliminate the space diagram to better visualize the vectors or the velocities acting on the link, and we can join all their origins to make a simple diagram of the vectors acting on the link. Again, as I mentioned, we can represent the vectors, we can represent the velocities using vectors, and these vectors acting on a single link can be represented by one vector. This one vector representation we can call as a resultant, and its vector we will call the resultant vector. All other vectors that contributed to this resultant we will call the components or the component vectors. When we add these vectors, these addends is the components, and the sum is what we call the resultant. So how do we do the vector addition? How do we determine the resultant or the one that can represent all the other vectors? We have three ways. We have the sum of two vectors using diagonal of a parallelogram method. So if we have only two vectors, we can use the diagonal of a parallelogram method. Also, if we have vectors that represent, if we will represent the vectors that are joining at each other's end, meaning after one vector, there's another vector representation, we can use the closing side of a triangle method. If we have multiple vectors, number 1 and number 2 is only concerned with addition of two vectors, while number 3 is addition of more than two vectors. We can use the closing side of a polygon method. How do we do this? For item number 1 and 2, if we have vectors, we have only two vectors, and if the vectors are represented whereas the origins are at one point, we can have the resultant vector by determining the diagonal of a parallelogram. So meaning, if we have vector here and vector here, and their origins are connected, let's make a parallel line opposite it. So in this case, this vector has a parallel line here starting at the end of the arrowhead of the other. So this vector has a parallel line here starting at the end of the arrow. So these intermittent lines, we can use it to enclose a parallelogram, and we'll just make a diagonal from this parallelogram to determine the resultant. So this diagonal line inside this parallelogram can represent the two vectors here. Okay, again, in vector addition, the purpose of vector addition is to have a single vector to represent the two vectors. So this vector diagonal is already an equivalent of these two.
So,
So if we have two vectors that is represented by joining their origins, let's make a parallelogram by having a parallel line opposite to each vector, which starts at the arrowheads of the other vector. So this vector has a parallel line. It starts at this one, and this one has a parallel line that starts at this one. We will have a parallelogram, and at the diagonal, by making a diagonal, we can have the resultant vector. Next is the closing side of a triangle. This is similar to the diagonal of parallelogram, but in this way, the vectors are connected not at the origin. They are connected by placing the next vector at the end of the first vector. So this representation, if we will have this as the first vector, the second vector is connected to the end of the first vector. Then, once it is connected, we will just close it to form a triangle. So that's why it's called closing side of a triangle. Then, this closing side of a triangle is our resultant. So these are similar. It's only the representation that differed, because in this representation, the origin or the tail of the two vectors is connected. But in this representation, the second vector connects from the end of the first vector. And we will just expand this statement number 2 if we have more than two vectors. So for example, we have 4 vectors. So if we have 4 vectors, definitely we cannot make a parallelogram.
Unfortunately,
So what we do to determine the resultant of these vectors is to connect the vectors at its ends. So how do we do that? Let's first select the first vector. So this one, I will use this as the first vector. Then the next vector, we will join at
mag-survey kung
its
sino yung
end.
gusto mag-avail ng
So this, I use this as the second vector, and its angle of inclination, I connected it to the first vector. Then I placed this as the third vector and connected this at the end of the second vector. And for the fourth vector, I connected it at the end of the third vector. So to determine the resultant, we will just have to connect from origin to the end of the vector.
for the cause, it's ranging
The arrowhead must be pointing here and not here, because this is the starting point. So we don't place the arrowhead at the starting point. Again, the reason why the arrowhead is pointing here, because this point Q is the starting point. This is the one which started the vector, the first vector, the second vector, the third vector, the fourth vector. So that's why the arrowhead is pointing towards here. Okay, so that's vector addition using closing side of a polygon. Subtraction of vectors, this is not usually performed, but still there's a sense here. Basically, the subtraction of vectors is head-to-head. Instead of joining the two vectors, by starting the second vector from the end of the other vector, what we will join is the two arrowheads. So the arrowhead of this one, this vector is here. The arrowhead of this vector is here. And if we join their heads, let's just join another and close it by using the closing of a triangle method. So this is the difference of these two vectors, this QA3. If you will ask, how do we perform subtraction by vectors of more than 2? What we will do, if we have, for example, 3 vectors, we will have first the difference of the 2 vectors, then that vector, the difference, we will use the difference with the other vector. So we will simplify first 2 into 2 vectors before we go to the other. Because by addition, we can just use represent all the vectors, then add it. And that's the difference between addition and subtraction. So resolution of composition of vectors. So by obtaining the resultant, we would use what we call the vector composition. Meaning, to determine the resultant, we would have first need to identify the compositions or the components. And in the reverse process, if we want to have the resultant be broken down into components, we will have what we call vector resolution. Okay? So if we have, for example, this vector, if we want to break this down into components, we will use the vector resolution. Let's make reference lines. So this reference lines is dependent on the designer. So if you want to have a different reference line, you will have a different composition. So for this example, if I want to determine the composition of this vector using these reference lines, I will first place the reference lines. Again, I would just like to repeat. When determining the components of a resultant, it is up to the designer on what reference lines he will use. So for this example, I use these red lines as the reference lines, and these reference lines will determine the direction of the components of this vector. So once I have made a reference line, these reference lines, I will have it have mirror or parallel lines here to make a parallelogram. So again, the first step I made to determine the components is to make reference lines. And these reference lines, I will have to mirror it or make parallel lines of it to make a parallelogram. So once I have made the parallelogram, the intersection points here and here will be our crucial reference. So once we have these intersecting points, we'll just have to connect the origin to these intersecting points. And once this origin is connected to this intersecting point, this length is now the components of this resultant. So that's how we determine the composition of a single vector. Again, you will have to determine on your own what is the reference lines, or if given, for example, I will be asking you to determine the composition of a vector. I will give which one is the guidelines or which one is the reference lines, and you will have to determine which is the components. So once we have determined the reference lines, we will have to mirror it. Yeah. Then, once you have determined the mirror or the parallel lines, you will have a parallelogram. And on the intersecting points of this mirrored line to the reference line, the intersecting point will be the reference line in determining the vector. Again, this green line is now the component. We have now determined the components of this vector with respect to these reference lines. So this vector can have a different vector or different components depending on which is the reference line. Okay, so in vector addition, if when I showed how to add by determining this, connecting the vectors, it is represented by this equation. So the plus sign must have an arrowhead on the right side. For a vector, it has quantities, magnitude represented by the length of the line as discussed on the parts, and the direction sense represented by the angle or the angularity of the line, and the arrowhead showing the sense. So because if we have an angle vector and there is no arrowhead, we don't know if it's going down or it's going up. So if we have the angle, we will still have the arrowhead to determine its sense. So that's it. That's it for today. I showed you. Bilis naman siya. Bitin pa kami. The Grashoff's law and the four-bar linkage and the vector operation. So for tomorrow, our topic is displacement analysis, position analysis, and we can start with instant centers. Okay. So again, thank you for attending the class. See you tomorrow. Have a great day.